This is week 18, page 1, problem number 6. It reads, write the expression for the solubility product constant for lead iodide, a solid. The first thing that needs to be done is to write the equation for the equilibrium of lead iodide that is separating into solution. We start by writing the solid on the left-hand side. The solid is the reactant. It's going to separate into ions when it enters a solution. If we look at the solid, the molecular formula for the solid, we see that there's 1 part lead and 2 parts iodine, or 2 atoms of iodine for every 1 atom of lead. So when we show it separate into solution, we have to show that for every molecule of lead iodide, we have 1 atom of lead and we have 2 atoms of iodine. We show that by placing a 2 as a coefficient in front of the iodine. Now usually when we write an equilibrium equation like this, we show that these particular atoms are ions by showing their charge. Now we know that iodine is in group 7A, so it can gain 1 electron. It will have a -1 charge. There are 2 of them, so the total charge of iodine atoms in the solution is -2, because each of the iodines has 1 negative. The lead has a +2, and we know that because it has to balance out the charges on the iodine. So we have a +2 and a -2, and that adds up to 0. The next thing we have to do is write the solubility product constant. Now the solubility product constant is written in a very similar way to the equilibrium constant. We take the products and we put them on the top of the fraction. And when we put them on top of the fraction, we make these little brackets around them to show that the number we're going to use here is the concentration of these particular ions in the solution. We take any coefficients that we see in the equation and we make them the concentration to the power of whatever the coefficient is. So here it's squared. Now when we would make an equilibrium constant, we would put the reactant on the bottom of a fraction. But we don't use a solid in an equilibrium constant. Neither do we in a solubility product constant. And therefore, in a solubility product constant, which is going to only concern ions in solution, we will only have the products multiplied, the concentration of the products multiplied together, and there won't be anything on the bottom of the fraction. This is week 18, homework sheet, page 1, number 7. It says write the expression for the solubility product constant for copper phosphate, a solid. The first thing again that we're going to do is we're going to show the equilibrium equation. We're going to place the solid on the left-hand side. We're going to use the 2-way arrows showing that this particular reaction is happening in 2 directions. The solid is being broken down into ions in solution, and at the same time the ions are being joined together back into a solid in the solution. So we have to write out the equation. So I start by separating the solid copper phosphate into its individual components, copper and phosphate. Notice that the polyatomic ion, phosphate here, doesn't get separated. It acts as one individual ion. Next, we are going to figure out the charges on each of these. You can look up in your book and find out that phosphate has a charge of 3 negative. We know over here from this subscript that there are 2 molecules or polyatomic ions here. So we'll add a coefficient of 2 to show that there are 2 phosphate ions. We know over here that there are 3 copper ions. Now, since the phosphate has a total charge of -6, we can see that by multiplying the coefficient by the charge. We know that the copper has to have a complete charge of +6. Therefore, it is going to have an individual charge of 2 positive. Now we're going to write the solubility product constant. To write the solubility product constant, we take the products of the reaction and we show their concentrations next to each other, which means that we multiply them together when we use real numbers. Each coefficient is made into an exponent. So the copper has an exponent of 3, the phosphate has an exponent of 2. And there we have our solubility product constant expression. This is week 18, page 1, number 9. A sample of cadmium hydroxide is added to pure water and allowed to come to equilibrium at 25 degrees Celsius. The concentration of cadmium ions is 1.7 times 10 to the -5 molar at equilibrium. What is the value of the solubility product constant for cadmium hydroxide? Again, the first thing that has to be done is the equilibrium equation has to be written. So we start with the solid on the left. Then we separate the solid into its individual components, and notice that hydroxide is a polyatomic ion and acts as one individual particle or ion. So now I've separated cadmium hydroxide into cadmium ions and hydroxide ions. The AQ, of course, shows that it is in solution on this side of the reaction. On this side, it's a solid. Now we have to remember that this 2 here means that there are 2 hydroxide ions. So we put a coefficient of 2 to show the 2 hydroxide ions. Now we know hydroxide has a charge of -1 for a total charge of -2, and therefore cadmium must have a charge of +2. Next, we're going to write the solubility product constant expression, and then we'll be able to place or to replace the terms with actual numbers. So you can see here we have the solubility product constant. It shows the concentration of cadmium multiplied by the concentration of hydroxide, which is raised to the power of 2, or we could say squared. Now we're going to put the actual numbers into this equation. Now the problem told us that the concentration of cadmium is 1.7 times 10 to the -5. It hasn't told us what the concentration of hydroxide is, but we do know whatever it is going to be squared. Now, you know that when cadmium hydroxide breaks down in solution, every molecule is going to yield 1 ion of cadmium and 2 ions of hydroxide. So whatever the concentration of cadmium is, the concentration of hydroxide will be twice that. So we can take the number that shows us the concentration of cadmium, we can multiply it by 2, and that gives us the concentration of hydroxide because it's going to be twice this. Now that we know the concentration of both of the ions, we can multiply these using the calculator. Be sure to square this side before you multiply it by this. When we square and multiply exponents, we know that we add the exponents. So we're going to, all of the exponents together, this, the negative 5 here, times the negative 5 here, times the negative 5 again. When you square it, you're going to have an exponent of times 10 to the negative 15th. When you multiply the numbers together, 3.4 times 3.4 times 1.7, you get 19.652. Now when we look back in the problem, we see that the numbers we're given here have 2 significant digits. So we're going to take this to 2 significant digits, and that will cause us to round up and have 2.0, or 20 times 10 to the negative 15th. Now this is not yet correctly put into scientific notation. We have to put the decimal here, and that will give us 2 times 10 to the negative 14th. I'll tell you a little way that I know what to do with the exponent when I move the decimal place. This is something I made up and I've used it for a long time. LA won, like maybe LA won the Super Bowl, Los Angeles, right sub 1. So whenever I move the decimal point left, I add 1 to the exponent. Whenever I move it right, I subtract 1 from the exponent. So here, the decimal point was here. I moved it to the left, therefore I added 1 to the exponent and got negative 14. Week 18, page 2, number 11. A sample of gallium trifluoride, a solid, is added to pure water and allowed to come to equilibrium at 25 degrees Celsius. The concentration of gallium is 0.049 molar at equilibrium. What is the value of the solubility product constant for gallium trifluoride? Of course, the first thing we have to do is write an equilibrium equation. We start with the solid on the left. We use the double arrows. We show each ion as part of an aqueous solution. We know that fluoride is in group 7A, therefore it has a charge of -1. If we look over here, we see there are 3 fluoride atoms. So we place a coefficient of 3 by the fluoride. Now that gives a total of 3 negative charges by the fluoride, so gallium must have a positive 3 charge. The next thing we have to do is write the solubility product constant expression. So the solubility product constant is the concentration of gallium multiplied by the concentration of fluorine cubed. We have been given in the problem the concentration of gallium. We have not been given the concentration of fluorine. But we do know that when gallium trifluoride breaks down in solution, each molecule yields 1 gallium ion and 3 fluorine ions. So whatever the concentration of gallium is, the concentration of fluorine will be 3 times as much. So we're going to multiply the concentration of gallium by 3 to figure out the concentration of fluorine. So the concentration of fluorine is 0.147, which has to be cubed when we do the math. So in order to figure this out, we're going to cube this number, then we're going to multiply it by 0.04. Notice that in the problem, the number given to us, 0.049, has 2 significant digits, so I rounded my answer to 2 significant digits. This is Wiki 18, page 2, number 14. Calculate the number of moles of barium chromate that must dissolve to produce 1 liter of a saturated solution at 25 degrees Celsius. The solubility product constant is 2.0 times 10 to the negative 10th. First thing we're going to do, the solid, we separate it out into its component ions. barium and chromate. Within this solid, there's only one part of each, so neither of them have a coefficient because there's only one of each. We know that barium is in group 2A, so it has a 2 positive charge, therefore chromate must have a 2 negative charge. The next thing we do is write the solubility product constant expression. Now, if we look at the solubility product constant expression, we can see that for every one barium ion, there is one chromate ion. Now, the problem hasn't given us any numbers for the concentrations of either of these, but it has given us the number that represents the solubility product constant for this reaction at 25 degrees Celsius. So we can solve the problem of figuring out the concentration of each of these ions. And then when we solve that, we can figure out the number of moles of one of those ions. Once we figure out the number of moles of one of the ions, that has to be equal to the number of moles of the solid, because for every one ion of barium, it came from one molecule of solid. So if there are 3 moles of barium, there must have been 3 moles of the barium chromate solid. Since the concentration of barium ions is going to be equal to the concentration of chromate ions, since there is only one of each per molecule, we can say that each of those concentrations can be represented by a variable, and as we usually do, we'll use the variable x. So the concentration of barium is represented by an x, and the concentration of chromate is represented by an x. If we multiply x times x, we get x squared. So if the solubility product constant is equal to x squared, we can replace that with the number we were given, 2.0 times 10 to the negative 10th is equal to x squared. Now if we take the square root of both sides of this equation, we can find out what x is, and that will tell us what the concentration of barium is. So we took the square root of the solubility product constant. It came out to 1.4 times 10 to the negative 5th molar. Now notice that the units we use in concentration is molar. It tells us how many moles of solute there are in 1 liter of solution. And that's how we measure concentration in a solution. Now, that helps us to be able to figure out how many moles we're talking about, because we know that molar equals the number of moles of the solute divided by the liters of solution. Oh, here's our molarity equation. The problem has given us some of the numbers. We found out here that the molarity is 1.4 times 10 to the negative 5th, and the problem told us that there is 1 liter of solution. So this is the replacement for molarity. N tells us a number of moles, and we have 1 liter under here. So we have to get rid of what's on the bottom of the fraction by multiplying both sides by 1. That tells us that the number of moles of the solute is 1.4 times 10 to the negative 5th. And that answers our question. This tells us that the number of moles of either barium ions or chromate ions is 1.4 times 10 to the negative 5th. And as we said before, whatever the concentration of one of those is the same as the concentration of the solid that we started with. Therefore, the number of moles of barium chromate is 1.4 times 10 to the negative 5th. This is week 18, page 2, number 15. What are the equilibrium concentrations of dissolved ions in a saturated solution of indium iodate at 25 degrees Celsius? The solubility product constant is 1.05 times 10 to the negative fourth. As usual, we start by writing an equilibrium equation. So we start with the solid indium iodate on the left. We break it into its individual ionic components. We have indium and we have iodate, which is a polyatomic ion. We know that indium is in group 3A, so it's going to have a 3 positive charge. Iodate, has 3 individual parts per every part of indium. So we put a coefficient of 3 here because this subscript shows us that there are 3 polyatomic ions here. The coefficient of 3 goes there. So we know for when this particular solid breaks down in solution into electrolytes, there will be 1 indium ion for every 3 iodate ions. Next, we're going to write the solubility product constant expression. The expression shows the concentration of indium multiplied by the concentration of iodate, which is cubed because we take the coefficient and we put it as an exponent. Now, the problem hasn't given us any of the concentrations, but it has given us the solubility product constant. We know that we can replace each of these concentrations with a variable. Since there's only 1 indium, we'll replace indium with an X. For every 1 indium, there are 3 iodates. So we can call iodate 3X. Now we've replaced these 2 concentrations with variables. We need to be sure to keep the exponent. Now, we need to combine this into a more usable form. So I wrote out the x cubed as 3x times 3x times 3x, and I put the x here. If you notice, there are 4 x's being multiplied, therefore the x is going to have an exponent of 4. 3 multiplied by 3 is 27. We can now replace the solubility product constant with the number that we were given, and we can show that it is equal to 27x to the 4th power. Now we have to figure out what x is. We're going to start by dividing both sides by 27. And we see that x to the 4th power is equal to 3.89 times 10 to the negative 6th. Now we have to take the 4th root of this to find out what x is. So we find out that x equals 0.0444 molar. Now we know that we said indium, the concentration of indium is represented by X. So the concentration of indium would be this number that we came to. The concentration of iodate is 3 times the concentration of indium. When we multiply the concentration of indium by 3, we get 0.133 molar for the answer to what is the concentration of the iodate ions in this particular solution. This is week 18, homework sheet, page 3, problem number 8. A solution is prepared by dissolving 0.010 grams of gallium trifluoride in 100 milliliters of hot water. Will a precipitate form if the solution is cooled to 25 degrees Celsius? Assume that a negligible change in volume occurs during the operations. The solubility product constant is 1.6 times 10 to the negative 4th. The first thing that we do is write an equation for the dissolution of gallium trifluoride in solution. In other words, we're going to write an equation for what happens when gallium trifluoride is dissolved in water. We see that gallium trifluoride dissolves and separates into 2 ions, a gallium ion and a fluorine ion. Gallium ions have a charge of +3, fluorine have a charge of -1. We see from the molecular formula that there are 3 fluorines for every 1 gallium, so we need to add a coefficient of 3. Now the equation is balanced. We have 1 gallium here, 1 gallium here, 3 fluorines here, 3 fluorines here. The next thing we need to do is find out the concentration of each of these ions. The next thing we need to do is find out the concentration of each of these ions in the solution. We know that concentration is always measured in molarity. Therefore, we need to figure out the molarity of each of these ions. And we have the molarity equation. Molarity equals moles of solute divided by liters of solution. Now our problem gives us the amount of gallium trifluoride in grams. Therefore, we're going to have to convert the grams of gallium trifluoride to moles. So we have 0.01 grams of gallium trifluoride. We multiply that by a fraction which has moles on the top and molar mass on the bottom. I've calculated the molar mass of gallium trifluoride here. The molecular mass of gallium is 69.7. We have 3 fluorines, and therefore I add the 19 in 3 times. That gives us a molecular mass of 126.7 grams. That goes at the bottom of the fraction. When we divide, we find that there are 7.9 times 10 to the negative 5th moles. Now that we know how many moles of gallium trifluoride there are, we can use that number to figure out the concentration of gallium ions and the concentration of fluorine ions. So for the concentration of gallium ions, we know that there's only 1 gallium ion per molecule of gallium trifluoride. And we know that there are 7.9 times 10 to the negative 5 moles of gallium trifluoride. And for each mole of gallium trifluoride, there is 1 mole of gallium ions. So we can use that number of moles. Then we're going to divide by the liters of solution. The problem gave us 100 milliliters. In order to convert milliliters to liters, we use this fraction, 1,000 milliliters over 1 liter. And now we know the concentration of gallium ions has a 7.9 times 10 to the negative fourth molarity. Now, since there are 3 fluorine ions for every gallium ion, the concentration of fluorine is going to be 3 times the concentration of gallium. So we multiply 3 by the concentration of gallium ions and we get 2.4 times 10 to the negative third for the molarity or concentration of fluorine ions. Now we can find a solubility product expression for the concentration of gallium ions and fluorine ions. Remember, the fluorine ions have to be cubed because over here we have a coefficient of 3 for fluorine. Then we can find the ion product. The ion product is the concentration or molarity of gallium multiplied by the molarity of fluorine, which is cubed. First thing I do is cube the fluorine concentration, and I get 1.4 times 10 to the negative eighth, and then we're going to multiply these two. It turns out that the ion product is 1.1 times 10 to the negative 11th. When we compare that to the constant given to us in the problem, which is 1.6 times 10 to the negative fourth, we see that Q is much less. Q is less than the solubility product constant. Therefore, we know that this particular solution is not saturated, and if it's not saturated, then it will not form a precipitate. This is Week 18, homework sheet, page 3, number 9. A solution is prepared by dissolving 0.0001 moles of zinc hydroxide in 50 liters of hot water. Will a precipitate form if the solution is cooled to 25 degrees Celsius? Assume that a negligible change in volume occurs during the operations. The solubility product constant is 4.5 times 10 to the negative 17th. Again, the first thing that has to be done is writing the equation for the dissolution of zinc hydroxide as it dissolves in solution. So here we have the equation. Zinc hydroxide yields zinc ions and hydroxide ions, and the AQ shows that it's in solution. Now we notice that the hydroxide has a charge of -1, zinc has a charge of +2. If we look over here at the molecular formula, we notice that there are 2 hydroxides for every 1 zinc. Therefore, we have to put a coefficient of 2 in front of the hydroxide. The next thing we have to do is figure out what are the concentrations of each of these ions when the zinc hydroxide dissolves in solution. Therefore, we're going to use molarity. Concentration is usually given in units of molarity. The problem tells us that there are 1 times 10 to the negative fourth moles of zinc hydroxide. And we know that there's 1 mole of zinc for every mole of zinc hydroxide. Therefore, there's going to be 1 times 10 to the negative fourth moles of zinc. So in order to find the concentration of zinc, we say there are 0.001 moles of zinc per 50 liters of zinc, and that gives us 2 times 10 to the negative 6th molar concentration of zinc ions. We know that there are 2 hydroxide ions for every 1 zinc ion. We can tell that because there's a coefficient of 2 here and a coefficient of 1 here, so 2 to 1. Therefore, we can take the concentration of zinc and multiply it by 2 to give us the concentration of hydroxide. Now we'll write a solubility product constant expression. So the solubility product constant expression is going to be the concentration of zinc multiplied by the concentration of hydroxide, which is squared because of the coefficient of 2 by the hydroxide in the equation. Now we need to find the ion product. So the ion product is going to be the concentration of zinc multiplied by the concentration of hydroxide, which is squared. The first thing I'm going to do is square the hydroxide concentration, and then I'll multiply it by this to get a final answer. And our ion product turns out to be 3.2 times 10 to the negative 17th. If we look at the problem, we see that the solubility product constant for the dissolution of zinc hydroxide is 4.5 times 10 to the negative 17th. Therefore, our Q is less than the solubility product constant. Start over. When the ion product is less than the solubility product constant, it is not a saturated solution, and therefore it will not precipitate.